So welcome back, everyone. Now we're going to have an open discussion with Roberto and John, and you can ask them as many questions as you like on the talks and beyond. Also broader questions involving the interactions between their research topics. So, is there any question in person or online? Faye.
I think you said that at the very beginning, when you said first that the main organizing principle is the uncertainty, and then you said effectively the framework that you were working within is one in which you assume that the high energy theory is local.
No, I'm sorry. Yeah. So I guess I let me say it again. What is that the unknown when we live at low energies, the unknown effects from a high energy theory appear local to us because so that their effects on the low energy physics are local terms in a Lagrangian. So that's the distinction. And so what this is an amazing organizing principle in a way, because it organizes an infinite number of unknown high energy theories into a few constants. And to do calculations at a given order, you only have to know a few of those. It's only when you insist on going to all orders that it becomes a problem. So it's a reduces infinite unknowns to a small number of constants.
Yeah, I mean, it is the framework. It's an assumption.
Well, it's an assumption, but the main assumption is basically the uncertainty principle. The rest of it is just the usual filters. I mean, it assumes that we have a four-dimensional theory that's approximately flat and all the usual assumptions. But the main extra one is really just the uncertainty principle.
So when you say uncertainty principle, you mean that large distances correspond to high energies?
The short distances correspond to high energies. So that the high energy effects, because they're from high energy, look to us to be short distance. And the correspondingly, the stuff that comes from the low energy part can be long distance. And so you can separate out knowns from unknowns by doing local versus non-local. That's how you organize an explicit calculation in the effective field theory. You do loops, you renormalize the local coefficients, but you don't make any assumptions about them. You go out and you measure them if you're living at low energies. But the residual predictions come from the long distance behavior, which is typically logs and square roots of q squared.
Roberto, do you want to add something or okay? Then I see there is a question by Renate.
Yeah, I wanted to ask you about the scalar field model, part 3 of your talk. So did I understand correctly? So there is just kind of a global metric mode there. Your R, that was the curvature of the visitor space.
Yes, so there is a dynamical metric, but the only degree of freedom I keep of the metric is the radius. So I impose maximal symmetry.
Yeah. That's right. So it's a bit of a curious model, right? Because that makes it very global.
It's like mini superspace of.
Yeah. That's right. But then you consider the couple model.
Yes.
Cis, if you like, on the metric modes, they're frozen in, apart from the global one that you let be dynamical.
Yeah, but that is the mode that usually is affected by the cosmological constant, the global, the overall scale.
Again, on large scales, and if you're thinking of some local dynamics, like matter dynamics, that interacts with local metric.
Yeah, so you have these modes, And as the quantum number of the modes increases, of course, the modes have higher and higher frequencies, so they become more. But by the way, I didn't mention this, but when you have a scalar field and you put a cutoff on the number of modes, this is what in non-commutative geometry people call fuzzy sphere. And it's a model of a geometry that is goes a little bit beyond the standard commutative geometry.
Geometry, I'm not exactly sure what it does. I'm just pointing out that it treats the matter part and the geometry part very, very differently. So if one finds, I don't know, if you just give it as a kind of effective cutoff and don't give it too much of a physical interpretation.
In fact, Martin Reuter, he doesn't like to talk so much about the cutoff. He talks about sequences of gravity-coupled approximants, he calls them. So each one of these theories with a fixed n, finite n, it has a finite number of modes, and he wants to think of it as a system that in principle could exist as a physical system. So you have you see what I mean?
Cannot envisage that's what that system is.
The system consists of the first n modes of a scalar field without having any other. And this is coupled to a metric. And the question is, what is the metric that solves the equation in the presence of this matter field? And the point is that as you add more modes to this field, the metric that solves the equation becomes flatter and flatter.
Yeah, but does it tell me anything much about dynamics of gravity? That's just what I'm questioning, because you're just by hand freezing in, if you like, all the other degrees.
Well, it doesn't tell you anything about that. No, I agree. It just tells you what the global scale of the metric does.
Does it? So, very small additional question. So, does R have to be? R is positive. I mean, your capital R.
R is positive and constant. Yes.
Just as well. Are your equations also valid for negative?
Among the papers that I listed, they've also studied what happens on a hyperboloid. This is all Euclidean, so negative R corresponds to some hyperbolic type of space. And then the spectrum is continuum, but still you get a similar effect. As you increase the cutoff, this hyperboloid becomes flatter. Also in that case.
Okay, so there are three questions. Jan was first, Faye, and then Thomas. Oh, okay.
So the way that questions are organized in philosophy talk is that people have questions, yes, and people put up their hands.
Mhm.
But if you have a follow-up question,
Yes, that is a good point. So let's do.
finger.
Yes. So one finger is new question. 2 fingers is follow up. Okay.
Oh no, hand is a new question.
Okay. We can also use different conventions.
Finger
Yes.
is, I'd like to say something about this, the discussion we're currently having. So this is follow-up, but this is, I have a new question.
So fingers should have priority.
No, I don't need priority. But I don't.
Mhm.
Yeah.
Who was the first to follow? So you wanted to follow up, right? Or
But I was first, I have a follow-up.
okay, so Jan was the first to follow up. Okay, so from now on, new point, hand, follow up, 1 finger, and I go by first come, first served.
And if one disagrees, one.
Yeah.
No, I mean, it's more actually a comment to this discussion, because exactly the same point about this mode cutoff versus geometry, the coupling between these two.
So in your talk, you state that they are decoupled, that N is independent of R. But you could phrase it more general and say you have a given geometry and you have some modes of your Laplacian in this geometry. And but now you are choosing an N before you fix the geometry.
Yes.
That will reflect very different things, and that becomes very close to what you say in the fuzzy sphere, because now the geometry will be a function of this N in some sense. So we had a long discussion about this in this conference in Paris, where Renata gave a talk, the work she did with Reuter about this, and people were attacking her very much exactly on this point, saying that, look, I mean, this N dependence, the way you do it, fixing N before you have started doing anything, it doesn't make too much sense, because you would have a geometry where this N is very good and another geometry where it doesn't tell you anything. And it's so I'm just saying that I don't have any particular point in this, but there is a subtlety there of this N being a physical thing.
Well, I think I am on the side of saying that N is a very physical thing, because you just fix the number of degrees of freedom of your system. Quantum mechanical degrees, I mean, there's a field, okay, but you cut off the field, so you just count how many oscillator modes do I have.
Yeah, but
and now you fix that a priori. What's wrong with that?
There's very much wrong with it. Well, that was the center of this discussion, because the number of modes, it doesn't reflect. I mean, if you have a geometry, this wiggles something. This number of modes tell you nothing about that. But if you have a flat geometry, it might tell you much more. So calling the modes number physical, because it's a number of wiggles, that depends on the background it's wiggling in. Well, I'm not referring to this discussion. I'm agnostic about it, but I'm saying there is a subtlety there. Okay.
Is there any follow-up finger? Okay, Thomas was first, I believe. So, and then Ivano can continue.
Yeah, I wanted to understand the framework a bit better of the computation. So do I understand correctly that the computation is a field theory computation? So there are no spin 2 fluctuations. So if it's a field theory computation on a force sphere, I was just wondering, like, if you had some extra bells and whistles, like maybe some fermions, there are these results of the last, I don't know, so many years where people actually were able to do exact calculations because they can localize. It's called path integral localization, where you can actually compute a partition function or exact things of it on a force sphere. I was wondering whether that should shed light on this.
But those are
These are important symmetries. They don't have to be super symmetries.
Yeah, no, I don't have any comment on that. But sorry, I returning to Jan. I agree with you that the modes that I'm including are the modes of a quantum field on the sphere. So the overall symmetry has been fixed. And if the sphere had some wiggles, the modes will change presumably, but presumably not a number. If you just have small deformations, I wouldn't expect that the numbering of the modes changes. Maybe the level, the energy levels would change, but not the number.
Yeah, well, I mean, again, you can say just take an interval and take a number of wiggles in this interval. It's an interval. It will give a bad description locally. If it's a small interval, if there are few wiggles, it might be a good description. So I'm just saying that it depends a little bit on the geometry, but I have nothing more to.
Okay, but.
And Ivano then wanted to follow up.
Yeah, but I mean, it's like basically a semantic thing. It was just maybe pointing out that the way to understand this. I think this N is supposed to be like how many eigenvalues I keep.
Yes.
So what changes if I change background? Not only the eigenvalues themselves, of course, but the degeneracies of the model.
Yes.
What you keep is the sum of the degeneracies up to the level N.
Correct.
This is perhaps one way to understand the dependency on the background.
Yeah.
Like more concrete.
Yeah.
Even small wiggles will very quickly wash out the nice spectrum on the exact situation?
They wash out in the sense that Ivana was saying. The eigenvalues will not be degenerate anymore, but you know, they will still be the same. I mean that under continuous deformations of the geometry, you can continuously follow how each eigenvalue moves, at least for small deformations.
Yeah, but you have the whole sphere.
Yes.
So if it bigger a little bit here, and bigger a little bit here, yeah, it's not as nice. I think that's what-
Anyway, with the
Okay.
sphere, we know how to do calculation, and when you're off the sphere, we don't know how to compute anymore. So
I see
it's
two
a
follow-up
hint, okay?
there, but Paolo raised first. Was that a new point or a follow-up?
No. Can I
You, yeah, I mean, is that a follow-up or a new point? Follow-up.
No, my question is, just a tree diagram. If you write the 3 graviton vertex and the 4 graviton and the 4 graviton scattering amplitude, how does it differ from the normal gravity in your theory?
Are we talking about which part of my talk? First, second?
You have this theory with torsion.
Okay, yes.
Now there you can compute 3 graviton at the 3 level.
Okay, so you have Lagrangian, which is R of the, so the Palatini Lagrangian, for example, you're saying. It is the Ricci scalar, not of the Levi-Civita connection, but of some independent connection. So it's a term that has one derivative of the connection and no derivatives of the metric. Now, at 3 level, this gives you some propagator, which is a bit strange, no? Because
But just the 3 level.
yeah, at 3 level,
It's quadratic in momentum.
yes.
Speed in line.
No, it's linear in momentum then. The R term is linear in momentum. Because it's just a curvature. A curvature has one derivative of the connection.
Okay, so we were still discussing about eigenvalues, and there were two follow-up. I think Jan was first, and then Thomas.
No, I only want to say, well, I already said to Roberto, but let me just say, I think this calculation that he reported is truly remarkable. Well, because it shows that you have a way to do quantum field theory, which is finite. Because for any n, this calculation is finite. I mean, and what goes to infinity is this log n, it cancels with the finite terms when you put in the R dependence on n. I think this is a truly remarkable, a very interesting result, because here's a quantum field theory, this is finite. Without, I mean, you can say n is a cutoff, but you can just say that I'm doing my calculations, and for some sufficient large n, and nothing will change. Isn't that right?
Well, the limit n to infinity is finite.
Yeah,
That's what,
so
yeah.
basically nothing will change. So you can
At least some quantities are finite in this limit. I don't know that everything will be finite in this limit, but okay.
but it is very different from a usual cutoff situation.
Yeah, yes.
Thomas.
Just a very quick comment. Also, it's not really a question, but regarding this discussion, people who are doing QFT on support spheres also added at some point squashing parameters for which computations can still be done exactly.
Okay.
And then you can also check whether it's stable with respect to the Einstein equations in other directions. And if you want to say something, perhaps I don't know about these eigenvalue issue, right?
Okay, I take this as a suggestion of further work. Thank you.
Whether you've seen this or not.
No, I know that you can swash. I wasn't aware that you still know exactly the spectrum, but yeah.
Okay, more follow-up on this point, browser online. I don't know if there is anything. Okay, then new topic. There was Shravan first.
10 questions.
One.
So the question to John. So what you mentioned during your talk is about the uncertainty principle, Penrose diagrams, and light cones lose the meaning.
Yes.
I generally agree with this, but what I miss the detail is when you say about causality. I mean, how the commutator for phase like distances changes.
Right. Well, so my comment on causality is somewhat vague in the sense it mainly motivated by the fact that I'm having trouble defining light cones in such a theory, that the trajectories of massless particles don't seem to follow the same pathway for all particles. So that I would expect that if I'm trying to define what the commutator does outside the light cone, I have to define which light cone I'm talking about. And so it's more a sense of our usual definitions of how we do causality in field theory are need to be modified. I'm not making a suggestion that the effect of field theory is causal. And so it is, as far as we know, only giving causal properties, and any causality violation that might appear from having coefficients that come from UV theories without causality is apparently hidden. There's work to show that you can't see that any causality violation there. So there's nothing that's going to show causality violation at low energies, but it does have within it calculations that show that our usual definitions of causal structures at high energies must be modified in some way.
And do you expect any modifications to the uncertainty principle? I mean, there are several proposals of generalized uncertainty principles in some motivations.
If we restrict ourselves to well-behaved spacetimes, I would not expect it, because basically then I can, for most well-behaved spacetimes, you would expect that if you're relatively short distance, that you can use a metric where it's flat, and then I can use the usual uncertainty principle in that region. There are potential difficult technical difficulties of doing any quantum field theory in a curved space-time over very long distances where the metric changes dramatically over long distances. But at least the short distance structure, I would think, would be the same as long as the space-time is relatively smooth.
Different topic? No, then follow up first.
Yeah, it's sort of a follow-up, yes. So then, would you say that the equivalence principle is a sort of a classical accident?
So the equivalence principle is, of course, has very many different definitions. If you say that all massive objects fall independent of their internal structure, that probably would be modified. There would be different particles would behave differently, but in a sense, the equivalence principle is really the motivation for general coordinate invariance. And if that's what you mean by the equivalence principle, that's not modified. And so I would, the answer to whether the equivalence principle gets modified is difficult because there are many different equivalence principles. The equivalence principle should say that the bending of all massless particles is the same. It isn't, so that version is not, doesn't survive. But there might be versions that do survive.
And Roberto has a
This is related to what Renate was asking you earlier. You said that there's no geodesic motion, but when you do this scattering experiment, you only know what is the initial direction and the final direction,
Right.
for initial momentum, final momentum. You're not supposed to ask what happens in the middle. So you don't know whether it's geodesic or not. But perhaps the question you can ask is, when you look at the scattering of particles with different spins, you can ask if there's an effective metric that would give a geodesic motion that gives them all the same deflection. And the answer to that is no. Right. Yeah. So you can't define a quantum effective metric in some sense,
That's right.
such that all particles follow geodesics of that metric. So in that sense, and I think that is the most essential or the most basic formulation of the equivalence principle, and that's violated.
But the effective metric would be the gauge dependent, no?
Not
Would
gauge,
the-
but no, it's not a gauge question, it's a physics question. Different particles follow different geodesics. Even if they were geodesics, they would follow different geodesics.
We don't have a definition.
Hmm?
We don't have a definition in quantum
Yeah.
because we're integrating our geometry.
Yeah, sure. But
Yeah, it's just that I mean, if you gain some gauge dependence in the effective action and you define the effective metric to be solution to the effective action, then you inherit the scheme dependence.
no, but so you can, like I was doing in my third part of the talk, you can calculate an effective action, and then already David was saying the variation of that quantum effective action gives you quantum equations of motion, and then if you can find a metric that solves that equation of motion, you can call it in some sense some quantum metric. But what I think that what John is saying is that you can't interpret that metric in the usual way that every particle will follow geodesics in that metric.
Okay.
I think that is gone.
That sounds, I agree.
Yeah.
Follow up, Fawad.
Would you say that maybe different spins see different effective metrics?
Well, it's all. We can also calculate the motion of massive particles, and they're yet different and spin independent. In those cases, we've calculated the spin dependent corrections to that. But if you do massive particles, you get yet another answer for what the effective metric would be. So if the effective metric is different for every single situation that you're doing, then it's probably not a useful description. In a way, this isn't that much different though than E&M. We don't talk about the quantum corrected electromagnetic field around the atom. You calculate observables, and the metric itself is not going to be an observable in quantum gravity, and so this is a calculation that reinforces that.
Probably it's not very surprising because effectively the notion of metric for a field comes not from gravity but from its own equation of motion.
Yeah.
You write the equation of motion for the field, extract the kinetic term, gives you an effective metric for providing for accounting propagation. So if equations of motion get corrections in different ways quantimechanically, then maybe it's not
too surprising in the end.
Yeah.
It just that this is a calculation that reinforces that because it's an explicit calculation.
Faye, I think was next.
Correction is suppressed with respect to the classical
Yes.
deflection
Yes.
by the square of the Planck length divided by the
Distance.
impact of the ground.
Yes.
So in order for that to be measurable or
Yeah.
meaningful, physically meaningful, the impact parameter has to be very tiny amount of units.
Yeah. Exactly.
Few Planck lengths.
Right.
Is that, could one say, well, that's just, we don't believe in lengths of the meaningful length of that order anyway. So it isn't observable.
Right. So this is just the position space of partner of the fact that the amplitudes blow up at high energies. And so in fact, what we're doing when we form these quantities, we're basically taking Fourier transforms of amplitudes in momentum space. And so what's that's reflecting is the fact that the amplitudes are blowing up at high energies. And that's that's really where the problem lies, is it's the high energy behavior of amplitudes. This is just a way of visualizing that. But I think the fact that the amplitudes themselves get large at high energies is a real problem. That's where the problem lies, and this is just a reflection of that.
And then there were a follow-up by Renate, and then yeah.
Yeah, continue on the same theme. So, well, if I would say, if I would draw from what you've shown, I mean, the geodesics,
Yeah.
The impossibility of, say, having meaningful, let's say, physical two-point functions in quantum gravity that depend on something like a geodesic distance. Well, that I would find that quite disturbing, but perhaps that one cannot draw such an easy conclusion because, well, I don't. One of the reasons is just well, I was working with some approximation in an ill-defined perturbation series.
Right. Well, I mean, the perturbation series, I think, is relatively well defined. When you get to the edge of it, when you go to the place where the effective field theory falls apart, that's where I don't know how to do the calculations often. And so I'm just extrapolating from regions where I know how to do the calculation to regions where I don't.
Yeah, but I'm thinking, of this kind of perturbative two-point, physical two-point functions that some people have done in
Yeah.
context of QFT on
Right.
backgrounds, working with geodesic distances, because if you end this trouble, certainly in a technical sense, but would you expect the same kind of issues to appear, depending on what kind of particle I'm looking at? I mean, here the difference might be between something that's actually physically defined. So it's physically defined, and it depends on something I call maybe quantum geodesic distance. If this depended then on the time of matter, then I would really say a very, very fundamental part of the classical theory is simply not to be found in the quantum machine.
Yeah.
That would be something. That would
Yeah,
be very
thank you.
fun.
I don't know exactly how to answer it. But...
So we have a first follow-up here, and then Jan, and then a new point by Damiano.
My intention with the question about the equivalence principle was actually to go in that direction and question whether it will make sense to be holding a geometrical picture. But I realized under the discussion that there's possibly another solution, which is that the particles, when you take quantum effects into account, they aren't point particles.
That's right.
So they are sensitive to tidal effects
Yes.
and all of that. And they shouldn't, even if there was a metric that was common to everything, they shouldn't follow the same path because they are subject to tidal forces as well. So maybe
Right. I think in the sense that you're seeing the gravitational effect of this massless particle at a long distance away from it. Not just here, it's a long distance away, because the particles that couple to it and it itself can propagate long distances. So it's from that you say it starts looking like a usual. I mean, that's the type of things you see in field theories. It de-emphasizes the geometry part and emphasizes the field theory part.
yeah, and some of that field theory part is you can attach that to the property of the individual particle of field.
Right.
Maybe that helps in organizing your thoughts.
Well, yeah, I just want to make a comment that all this discussion can of course be made about two-point functions, to what extent they exist, and so on. Many areas of all quantum geometries, and of course be answered explicitly by analytic calculations in 2D. And in 2D, I mean, the result is that everything works fine, but it's truly non-perturbative if you want to define a two-point function which depends on some distance, because what is this distance? I mean, you can put a distance into the path interval, and you can claim this is the geodesic distance for all metrics there. Then you can take it outside the path interval because it's the same for all metrics. And you get a two-point function which depends on this geodesic distance. And this can be calculated. And you can even expand around geometries in 2D quantum gravity. If you have a cosmological constant, you also have a background there. You can expand around that. And you can see that adding tadpole diagrams and all kinds of things like will add up to something which is not similar to what is in flat space. Because we know that I mean, the two-point functions of vertex operators in this series are different from the similar vertex operator in flat space by the famous KPZ scaling relation. But you can understand that this is a beautiful work of the Samolotnikovs, that you can actually do perturbation theory, but you have to sum infinite subseries in order to get to this. So it can all be answered there, and there in 2D, but 2D is of course special because it is special. But it's the ultimate quantum gravity theory because there is no classical action. So it's all quantum, and nevertheless everything works. So just to put a positive thing on it.
Okay.
Yeah. Okay.
Then we have a new point by Damiano.
I'd like to ask some questions about the physical defined.
Oh, one of us. We have to fight over.
Okay. I guess. Normally people think that not even the running coupling is feasible, or the data function we can compute from UV derivatives, the usual one is not feasible. Normally it is spin independent at one, very rarely it is spin independent at two, but it will not be on that. As far as I understand, your computation concerns the 2-point function, right? And you compute the 3-point function.
For gravity.
Or any model. How do you can you guarantee that the structure you collect into the running couplet from the 2-point function will replicate in all the correlation functions like you have in the count semantics? How do you guarantee that your theory is really free in that limit? I'm just thinking, and didn't have enough time to elaborate on my own questions, so I took the time of the other discussion.
I mean, I think the answer that at least I gave myself on that is that Roberto and Diego were the ones who did this, showed that the form that we get is covariant when you add all the physical running. And so Roberto mentioned this in the talk that the coefficients that you have are not separately covariant, but when you add it together to get the physical running are covariant. And that to me tells me that all the vertices that come from, so this is in a background field method, we've got a covariant action with a running coupling. All the vertices that come out of that are going to share the same running.
I understand that, but that is based on the assumption of locality, right? So in a 3-point function, Gauss-Semantic equation works no matter how the correlation function, which is non-local, so it has a very complicated structure. Yet you know that inside you can isolate the explanation that always bring up the running couple that goes to zero. So I see that hard to use inside correlation functions because you do not have the locality there. And I assume that when you study logs like that in 3-point functions, you will have mixing between log of p minus q squared, log of p squared, and log of q squared with several momentum.
Right. So the assumption is that we're keeping all the momentum of the same order. They're all the p squareds are independently of order e squared. And then this is running with the overall scale of the problem. You have to take all momentum to be large and of the same order. Let's have Diego answer.
There is a follow-up by Diego.
If you want to consider the prefactor function, planning, you have to consider also non-local operator like R1/box R squared. Also, they will give a contributor to the prefactor function at the same order as the local term.
Yeah, but my question is mostly about, you're claiming that the theory is asymptotically free, right? That's your claim.
The couplings run to asymptotic freedom, yes.
Yeah, but that's a different thing, I would say. So if it is asymptotically free, that's a very strong claim. It should be seen in a correlation function. You should have a way to have control of the correlation function, which normally you do by means of a Gaussian equation. By rescaling, and that's just an overall rescaling, I agree. Because Gaussian equation is not very powerful in itself. But and so, for example, if you claim that the theory is free, what is the free theory then?
Well, so the claim that the theory is free is tied up with the trouble that we've run into with the fact that the high energy behavior still, because the momentum dependence that follows from the local Lagrangians yields a growing power law dependence that's multiplied by a coupling constant. And we've calculated the running of the coupling constant that's logarithmically going towards zero, or can, if you choose your parameters right, run towards zero. It's not saying that the interactions are getting weaker at high energies, because it's multiplying a term that has power law growth, and powers beat out logs all the time.
But they're not claiming that interaction.
We're not at this stage claiming that the interactions are there. We're claiming that the coupling constants run to zero. I have to admit, I didn't appreciate the distinction until we started discussing what's the meaning of our results.
There was a new point by Israel.
Yeah, just a good question. What do you mean that like we start with John's talk where you mentioned about EFT, that you gave it from EFT to full TV, and
yes.
you gave an example where the full TV does not read that EFT terms. I'm just wondering, like, I'm asking this in a proper way. Do you think we are writing too many EFTs that are unnecessary for the theory?
Well, I mean, the theory that I had an EFT at low energies. And so if you were doing low energy physics, then you had to use that EFT, or you should use the EFT. And it's the right low energy description, and we live at low energy, so we should always do that. But it is a interesting point that some of the features that we do in the EFT disappear and change when we do the full theory. Now, Roberto's pointed out to me that this happens all the time, and let's take the linear sigma model. The linear sigma model has a low energy EFT, and in fact, this shift invariant theory is the sigma model for the U1 sigma model, the linear sigma model. And then the full theory is the sigma model, which is none of these troubles. And so there are theories where you have effective field theories with all these powers, and it turns into a nice, well-behaved, renormalizable field theory at high energies. What's different here is it's turning into a renormalizable field theory that still has powers in the interaction, and the same degrees of freedom. So there's something new, but something is also what we would have expected.
Follow up?
Yeah.
Okay.
Well, just a little addition to what John just said. If you consider the theory which has only two derivative kinetic term, then it's non-normalizable because the dimension of the coupling. And so when you construct the amplitude, well, then you can treat it as an effective field theory. And all those terms that he called G6 and G8, you know that they're going to be present, but you cannot calculate them. They're free parameters, basically. Whereas if you see this as coming from as a limit of the high energy theory, which is renormalizable, the one which also contains a box phi squared, then in this case, the G6 and G8 can be calculated in terms of the G itself. That's the main difference.
You mentioned kind of different topics. For example, you mentioned the unimodular gravity and the metric affinities, but the main point is that ultimate goal is to get a UV complete theory and renormalizability and go to but then these frameworks, MAG is quite more complicated. So how does this new effects like torsional non-metricity or if you demand something else like unimodular will help for UV physics? So.
No, I don't think that they help at all. They will just make the problem more complicated. And at best, they're going to behave in the same way as the metric theory does. But the motivation for that was not to have a UV completion. The motivation is to have something that is more similar to what we know about the other interactions. Yeah.
Yeah. So I see some new points, but let me exploit my chair power to follow up. So indeed, I was also confused about the same points that Shravan mentioned. So you discussed, well, first, what is effective field theory problem? We have infinitely many parameters problem, not normalizable, but this is really a feature of effective field theory, not a bug, is how we parameterize theories at low energies. So it's perfectly fine that we have these features. But then you said, okay, let's go to the full theory, but the subtle or more complete story is that there isn't one full theory. So in principle, one can UV complete in different ways, and there is some equal effect. But if we find something from the input of the full theory that we do not expect from effective field theory, or that is problematic from the effective field theory perspective, perhaps this tells us that the full theory we are considering is not the right one. And a related point to this was, I don't know if I understood correctly, because I was also far from the whiteboard, so I was not sure I was seeing correctly, but you were already using at that level the inverse Feynman prescription, right? And perhaps the fact that one gets any contradiction with the effective field theory could tell us that something goes wrong, either with the UV completion or with the prescription to quantize.
So I guess if the UV theory contradicted the effective field theory, yes, I'd agree. In some ways, the pathway that I described has the usual effective field theory at low energies. The only things that's a bit odd from it are that if you take some of these constraints that come from causality and apply them to gravity, it tells you that some of the coefficients in the effective Lagrangian should have certain signs. Mm-hmm. And these theories violate that. Mm-hmm. So it, but that doesn't violate the effective field theory. It's just a slightly different effective field theory. So I think these have a nice effective field theory description, but it's the high energy theory that I'm more worried about now.
Mm-hmm. Okay, so you say it's not really in contradiction.
It's
just
not in
unexpected.
contradiction to anything in the
Okay.
effective filtering.
Okay, that clarifies my point. And then there will be new point by Luca first.
Yeah,
And
actually,
then-
my question, I guess, is for both of you, is related to the high energy behavior of these amplitudes in the theories, in particular in gravity. Now, when we usually demand renormalizability for the order interactions, we get renormalizable theory, but also amplitudes that basically decrease at high energies. But if we take gauge bosons and we got Higgs, we can really renormalize and also unitarize the amplitude. And here, if we take quadratic gravity as a renormalizable theory for gravity, which is a unique renormalizable theory for dimension, we solve the problem of renormalizability, but we still have some growth in the amplitude. And this is, of course, a net distinction between, say, gravitational renormalizable theory and non-gravitational renormalizable theory with two derivatives. Of course, but for gravity, we really need higher derivatives to normalize. Now, of course, John presented like a possible way out. I mentioned a possible way out in the perturbative regime that is basically proposed by Holden, where he says basically some cancellation of Doppler in the perturbative regime. But to me, it seems that basically the fact that renormalizability is not enough, it seems to me that basically there should be something in gravity that maybe is not the interaction. And this something could be maybe some non-perturbative feature that will play a role. And indeed, we know, for instance, that in gravity we have black holes. That some people said to make expecting some high energy scattering, for instance, before, because basically you can confine high energy in small distances and so you can comprise of. And there are some people who think that, for instance, the high energy scattering between particles, for instance, in gravitons, at some point should basically be sensitive to this black hole formation. And some of these people also think that basically this effect may even like give in the end some amplitude, which is not growing anymore, but it will have some suppression. Now, I'm not really, I have many questions about this, but I'm glad to know your opinion. Like, do you think that maybe some non-perturbative effect of this type would kick in and basically tells you gravity is more special than the interaction and geometric is not enough? Well, it's enough, but we need to anyway add something more, maybe towards one scale, like some non-perturbative feature is there somehow.
So when you have the full theory, I guess you do have to ask questions about non-perturbative effects. I mean, we don't in the effective field theory because that's beyond, it's a perturbative effective field theory.
But I'm thinking like quadratic gravity.
Yeah, and so in quadratic gravity, you should ask these questions, and I don't know their answers.
Basically about UV perturbative weakly coupled theory
Right.
up to some scale, which could be M-Planck or M-Planck.
Right.
And then at some point, maybe some non-perturbative feature is seen. Because if you just take the Holden points of view, it looks like that at no energy, you will worry about black hole formation.
Well, so black holes are not described by two gravitons. They're multi-gravitons, and so basically you'd be asking questions about scattering into n gravitons with n going towards infinity for big black holes, and that's a different question than we've asked. It's not clear that couldn't be addressed in perturbation theory because there are techniques for doing 2 to n calculations. There are some that have been done for gravity, but it doesn't completely address the overlap of that n particle final state to a black hole. But presumably that's where the focus would be. Doing 2 to 2 scattering is not really the.
Because you can imagine an elastic process like 2-2,
Yeah.
Whereas an intermediate state you will get a black hole.
Right, so then you have to do, it's the equivalent of the old Reggie type calculations where the intermediate states there are n particle states, and
people expect some suppression basically.
Right.
But who knows, maybe.
yeah, so it's definitely worth being doing. I agree with that part of it. I don't know exactly how it comes out.
And actually, in one of your papers, I think, 15 years ago, maybe, you were in the framework of EFT,
Yeah.
you were asking the same question, like, improving compared to, by summing like perturbation theory and basically working with some rest quantity.
Right, so,
Do you think here will not work?
well, I mean, that was a very simple one. That was summing
Yeah.
vacuum polarizations. And the effect of that was just basically taking the infinite sum and putting it as a prop into the propagator. That's a particular sum that I know how to do, so I did it. You know how to do it. Everyone knows how to do it. This other is a sum over diagrams, which is much more complicated. The master of that was Lipitov, and he's no longer with us.
Can you follow up on this? Okay, if not, you had the new point, right?
Yeah, but
One-
it is sort of a follow-up as well.
Okay, that's good.
It's about high energy. And it's also a bit of a comment to John's question at the end, what is success?
Yes.
I don't know what it is. And maybe to elaborate on
But
that.
some content will explain.
Well, then I would
In 200 years,
investigate, but
maybe.
Another potential, you talked a lot about this problem with strong high energy behavior, and understanding that could be some sort of success. And then I'm imagining that there can be fine structure in discussing success, less success and more success. For instance, I don't think you can expect to have decreasing behavior at high energy, because you exchange one graviton, you exchange two gravitons, and they typically will be higher orders in powers of energy. So at least order by order, you always have large contributions that may cancel in some certain amplitudes, but there are strong interactions, and maybe the solution is not to have a decreasing, shouldn't be decreasing high energy behavior, but some understanding. And we even lack that in string theory, because it's the same. It's a feature of unitarity, essentially, that we will have all these multi-graviton exchanges.
Yes.
So that was the comment, and the question is then again, we haven't sorted this out in a theory which claims to have in principle control over all the higher loops. So is it something we should aim for, or should we have other lower goals for?
Right. So since this occurred in even a simpler theory than gravity, that's shift invariant theory that we started with. It's Roberto and Diego and I. That might be a place where we could imagine trying to understand the high energy structure better, without all the complications of gravity. So you don't have to answer about black holes, and you don't have to answer all those. That's the field theory. I'm present in a collaboration trying to put that on a lattice. And so we can maybe ask lattice questions. It's Euclidean, but nevertheless, you can ask lattice questions about that theory and see that it's stable, the interactions, the fact that there are ghosts in the Minkowski theory, and the Euclidean theory probably won't make anything unstable. What do correlation functions look like? So my motivation for getting into this lattice collaboration was to answer questions like that. What are the structure of such a theory? But I would hope that I could eventually come up with an analytic understanding of how the theory behaves at high energies that we could then imagine taking over to other theories. In the spirit of a workshop, let me stop there.
Okay. Neil.
Sorry, just to add to that theory, I think it is a very interesting theory. You did mention it asymptotically free, which is.
Well, so it depends on the side of the coupling.
Right.
So
Okay.
it can be asymptotically free or not, depending on the sign of the coupling. And I forget which sign is which.
Negative.
Negative. Okay. Thank you.
Okay, so I think this was a very nice discussion with very nice and open questions. So let's thank again the daily speakers. We now go for lunch.